Okay, I think we're going to go because I think it's starting. If it isn't, we'll find out. All right, so what I'm going to do is sort of briefly go back a little bit to chapter 7 and 8 to help explain chapter 9 and kind of where we're going from here. To review a little bit, all we're doing in chapter 7, and actually from this point on, are working with bell-shaped curves or normal distributions. We had uniform, we had exponential, we had binomials, Poissons, those are all done. We're just now dealing with the bell-shaped curve. And what we started in chapter 7 doing with the bell-shaped curve was saying, okay, if we take a sample, we're going to get a sample mean x bar that is at the middle of the bell-shaped curve. And then the first things we said were, oh, how confident are we, or what's the probability that we're plus or minus 5 of that mean? And by that I mean, this is a sample mean. It's just a sample from an entire population. So we don't know if our sample mean is an accurate predictor of the population mean. We think it is. If we've done good sampling techniques and the like, we think our sample mean should be really close to what the population mean is. It could be right on, it could be a little higher, a little lower, whatever. But we have to give some sort of confidence of how confident we are that that sample mean is within plus or minus some number of what we think the real population mean is. So let's say in this case we did plus or minus 5. And you might remember doing the problems, and you go through it and you find the z-scores that correspond with a plus or minus 5. And that z-score is going to be negative on this side of the mean and positive on that side of the mean. When you find those z-scores, you'll find an area from the left margin to here, the right part, and from the left margin here, the left part, and find that area. Let's say it's 50%. Okay? That's a way of evaluating how good your sampling is. Hey, I'm 50% confident, or I'm 50% sure that the real population mean that I'm predicting with my sample mean is within plus or minus 5 of that sample distribution. Okay? And 50%, frankly, isn't very good. That's a coin flip kind of thing. So what we would usually do is change the parameters a little bit and increase the sample size, which would give us a little bit of a different curve. In fact, as we increase the sample size, our curve becomes taller and narrower. And because we have this extra space here, which doesn't look like a lot, but in statistics it is, we then can say with that increased sample size that we are, let's say, 75% confident now. And that makes sense. You increase your sample size, you should feel more confident that your sample mean is a predictor of the true population mean. All right? And that's what confidence intervals are. We just want to say, okay, we're plus or minus some amount, and that's how confident we are. And that was chapter 7. Then in chapter 8, we did something a little bit different. Instead of the data telling us how confident we are, 50 or 75%, what we did in chapter 8 was say, okay, let's figure out what our interval is, our plus and minus. And when we're 90%, 95%, or 99% confident. So instead of going plus or minus here and finding the probability area, let's start with the probability area, work backwards and see what we are plus or minus, and that gives us our confidence interval. Okay? So it tells you what the value for x is here and what the value for x is here, such that you would be 90, 95, or 99% confident. Okay, so far so good? We're good? Okay? With that, because we have those constants, so to speak, we have some constant z-scores that we can rely on. Okay? And those constant z-scores for a 90, 95, and 99 are on the formula sheet for chapter 7 and 8, there's a box there, and it says common z-scores. So you see at 90%, the z-scores you're going to have here are negative 1.645 and positive 1.645. If you want 95% confidence, you're going to use z-scores 1.96 and negative 1.96. And if you want to be 99% confident, you're going to use z-scores 2.75 and negative 2.75. And sometimes the book goes 2.576, but that's just a rounding kind of issue. Okay? So with that, we're able to work backwards and find out what the values for x are, such that we're 90, 95, or 99% confident that our sample mean is a predictor for the true population mean. Okay? And what we're saying is, hey, we're 90% that it's between these two numbers based on the sample. At 95, all we're doing is actually making the target bigger. We're actually kind of cheating. Instead of this being 90, okay, this makes us 95 because we're making a bigger target. And if we make even a bigger target, 99, we'll be more confidence between those two numbers. And we're increasing the margin of error. And a margin of error is a term of art that we use in chapters 7 and 8 routinely. Okay? Any questions at that point? Does that make sense to you? Does that help a little bit in some way? You can't see this on the camera, but they're nodding yes. They're very appreciative. Okay. All right. So that's what we did in chapter 8. And we did that with sigma known. That's easy. When sigma known, sigma is the standard deviation of the population, as opposed to little s, which is the standard deviation of the sample. When we don't know the population standard deviation, we're going to use the next best thing we have. And the next best thing that we have is going to be a sample standard deviation. But realize that sample standard deviation statistic comes only from the sample itself, whereas the population parameter, sigma, is a known or historical value that we have a great deal of faith in. Because of that, we, instead of using z-scores, use the t-tables. And the t-tables are z-scores, but they're t-scores, and they're larger generally because they compensate for the fact that you're not using a population parameter, but a sample statistic, a little less. Okay? So you have confidence intervals the same with sigma unknown. You still have an x bar, a sample mean that you get from your sample, but instead of a z-score, you're using a t-score. Instead of sigma, the population known parameter, you're going to use little s from the sample, and the square root of n, the sample size, which is the same. Okay? And hopefully you remember from the lectures on the narrative PowerPoints and the like, that eventually when the sample size gets toward 100, those t-scores are almost identical to the z-scores of 1.645, 1.96, and 2.575. Okay? So get the idea that the t-scores are used because we're not dealing with a population parameter, something that's big, known, and established, but just data from a sample that can vary one way or the other. Okay? So that's when sigma is unknown and we use the t-score. That's the difference. When you use the z, when sigma is known. When you use the t, when sigma is unknown. A wrong answer is when to use the t when I don't know a standard deviation. No, you know a standard deviation, it's just which one? Yeah, the sample standard deviation. Thank you. As opposed to the population standard deviation, okay? So that's the key thing. It's not the sample size. Sometimes students say, oh, I use t when the sample size is less than 30. No, that's the central limit theorem having to do with whether or not we can assume a bell-shaped curve or not. The difference between using t and z has to do only with, if I know sigma, I use a z. If I don't know sigma and I have to use the sample standard deviation instead of the population standard deviation, I use a t. And the last one is proportions, which is just a relative frequency going all the way back to chapter 3. It's a fraction. It's a relative frequency. Okay? And with those, if you look at the formula, use a z-score, I don't even have a standard deviation in there, so it doesn't matter. I don't have to worry about sigma known or sigma unknown. I'm using that proportion, and I can do a margin of error and confidence interval the same. Okay? All right, so that sort of is a background into 7 and 8, and maybe stuff that you would have liked to have heard 2 weeks ago, but we didn't. Okay, that's fine. All right, water under the bridge. Let's move on. Okay? Now, the next thing is I'm going to go to Chapter 9 formula sheet, and this is on Blackboard. Blah, blah, blah. Okay, there it is. And what we're doing in Chapter 9 isn't different at all. In fact, we don't learn anything new at all about bell-shaped curves or z-scores or t-scores. We just apply what we learn into a method of hypothesis testing and decision making. So we use the bell-shaped curve to make a decision for us. A scientific decision, not based on, yeah, it looks good, looks close, isn't close, whatever. It's just the numbers. It's data-driven. If the number says this, we're accepting the null. If the number says this, we're rejecting the null. That's it. The first thing you have to do is set up that hypothesis test. And again, there's a formula sheet on Blackboard for you. And generally speaking, the null hypothesis is the status quo, the current condition. This is the way we've always done it. And I believe there's some quizzes and stuff you can do to set up that hypothesis test. And the alternative is everything else. So on hypothesis testing, you always have greater than or equal to in the null hypothesis. You have no equality in the alternative. It's either less than, greater than, or not equal to. Okay? And you set that up first. Those numbers for mu sub 0 are the same. So let's just make something up. Let's say the null hypothesis is the mu is greater than or equal to 100, and the alternative has to be everything else, so mu is less than 100. And if you write your hypothesis test that way, you can match it up here and you say, oh, I've got a lower tail test. Okay? What's that mean? That means I'm going to draw a bell-shaped curve, and it helps to draw the curve. I'm going to have a one-tail test, which means I only have one tail on my bell-shaped curve, and it's going to be at the lower tail. Okay? I'm going to have a critical value. Critical value is sort of the standard again, and it depends on if we're testing at 90, 95, or 99%. Those are the three we usually do. Every once in a while they'll throw in a 97 just to keep you honest, sort of thing. And let's say we do 95. Okay? If we have 95, how much, or what's the probability that's in that lower tail? Not negative 0.05, 0.05. Why is it not negative 0.05? This is an important point. I'm glad you said it. You said it on purpose so we can make the point, I know. Remember, there can be no negative probabilities. Probabilities are always positive. What can be negative is what? The z-score, exactly. Okay? The z-score is negative or positive. The probability is never negative. You always have a positive probability. Okay? So you have some z-score at 0.05. I'm going to look in my table, and I see that at 0.05, the closest value that I have is 1.645. 1.645, and here it's going to be negative because I'm on this side of the mean. All right? That is, and now I'm going to use the terms of art, just like you should. Okay? This is the critical value. The critical value is going to be 1.645, 1.96, 2.575.
What page did you find that on?
Okay. 730. This is the standard normal curve. And what I've did is I looked in the body of the table, because this is where areas are. That's where that green space is. And I'm looking for 0.05. And the closest number I have to 0.05 is 1.64 and 1.65.
Okay.
Because 1.64 is 0.505 and 1.65 is 0.495, 1.645 splits the baby perfectly. We only do that once in a while, okay? If you aren't equidistant between those two, just pick the closest number. All right? So in that case, I have 1.645, and in this case, I know it's negative because I'm on this end. All right? Good question. Next, when I solve one of these problems, I'm going to find the test statistic. And if you look at your formula sheet, the test statistic is the same regardless if you use an upper tail test, lower tail test, or two-tail test. It's a z-score. Okay? It's a z-score using x bar, that value for mu that you have in your hypothesis test. That's just square peg, square hole goes in there. Standard deviation, sigma must be known, and the sample size, square root of n. And you get a test statistic. That test statistic is, for most problems like this, going to fall either here on this side of the critical value or here on this side of the critical value. Okay? But again, as a term of art, the z-score is the test statistic. Okay? Let's use this right one here just for this. If I have this as my test statistic, which is basically a z-score, with that I'm going to have a corresponding area that corresponds with that test statistic and is in blue here, this area. That's the p-value. Okay? The p-value is the probability area that corresponds with a calculated test statistic. Does that help? Okay. And then we're going to run our two tests. The two tests tell us the same thing, and they have to come up with the same result. Hold on. Cannot start recording. Oh, good. Integrity, that's fine. Oops, gotta get on the right one. My integrity one says I can't record, that's fine. This one started already. Okay. I'm going to do two tests. It's the same thing. I'm going to compare critical value to test statistic and the critical value approach. I'm going to reject HO if the z-score that I calculated in my test statistic is less than or equal to the negative z at alpha, or negative 1.645. Notice it's negative here in that formula sheet because it knows on a lower tail test you're going to have a negative critical value, right? On the upper tail test, there's no negative there because it knows you're going to have a positive critical value on that side. It gets a little more complicated on a two-tail test because it just depends on which one you land in. If you land in the lower tail, basically you're going to replicate this. If you happen to land in the upper tail, then you're going to replicate that. Okay? Either one. And I'm going to compare that test statistic to that critical value and determine if I reject HO or accept HO. Then I'm going to do the exact same thing, but instead of comparing z-scores, critical values and test statistics, I'm going to compare alpha, which is 0.05, and this p-value that corresponded with my test statistic. And I'm going to reject HO if the p-value is less than or equal to alpha. Okay? I have to come up with the same result or I've done something wrong. Because it makes sense. You're comparing apples to apples and oranges to oranges. Z-score to Z-score, area to area. Okay? There are just two ways of doing it. Why do we do two ways? Quality control check. Sometimes the p-value is easier. Sometimes the critical value is easier. All those reasons. Okay? And then if we reject HO, what's that say? Okay, we reject HO. We've statistically determined that that's the decision we're going to make. We've decided that the mean is really less than 100. That's our decision. And it's based on data, not based on, I think so, yeah, that looks right, etc. And you also might come out with, say that your X bar from the data is 95. And you say, well, of course 95 is less than 100. Why do I have to go through all this? Well, you have to go through it all because we're evaluating based on the standard deviation, based on the sample size, based on the parameters. Is that enough of a difference to make that statistical decision? In our example here, it is. Okay? It's not always going to work that way. Okay? So you just sort of follow the numbers and you do what the numbers tell you. Okay? If I'm in the upper tail, it's the same thing except this thing is flipped around. into the upper tail, you're going to have a positive critical value. You're more than likely going to have a positive test statistic. In this instance, you're still going to have an alpha of 0.05, and you're going to have a p-value that is, using the right color pen here, blue this way. And of course, you have the issue of what's that blue area. Do not say, for example, 85%, because 85, if you use the t-value from the left margin here, that's the larger value. You're looking for the area in the tail, so that's when you do 1 minus, or the area in the tail. All right, and now she's saying, oh yeah. And then finally, we have the issue with the two-tail test of whether or not you double the p-value or not. And basically, your book, the way it's told you, said you always double the p-value to compare to the full value of alpha. Sigma unknown, same darn thing. Absolutely the same. The only thing that changes is instead of sigma, you're using little s. Instead of getting a z-score, you're finding a t-score. And instead of using the z-table, you're using appendix. There it is, a table 2, starting on page 732, the student's t-distribution, and based on degrees of freedom. So instead of a z, you're going to the t-table and utilizing that table. Okay? And if I need to, I'll go back and explain the t-table a little bit better, but for now, that's it. And then for the last one, proportions, basically the same thing, a different formula for calculating the z. Notice we're back in z because sigma known, sigma unknown doesn't matter. And you basically do the same testing criteria you would with sigma known. Okay? All right, any questions at all on any of that? Okay, I'm going to just stop this recording and then start it again because I don't trust how long these recordings save sometimes.